So, welcome back to the session, right. So, in the last session we discussed about the state transition matrix. We had seen the basic properties of state transition matrix and we had seen the one example of state transition matrix, and then we were observing the solution of homogeneous and non-homogeneous equation from state space analysis, right. So, today we would like to solve a little bit numerical over the previous concept. So, in today's session we discuss about the power series method, right. Then we will discuss about a Laplace transform method and diagonalization method and Cayley-Hamilton method, which will help us to obtain state transition matrix. So, these are the various methods. So, broadly we will focus on the power series, Laplace and diagonalization. So, Laplace method that we used in the previous lecture to obtain the state transition matrix we discussed already. So, we will focus on the power series and diagonalization method. After that we will discuss about the controllability and observability concept of the state transition matrix. Okay. Then we would like to start from this example. So, here this state space relation is given here, okay, and this is the A matrix, order is 2 cross 2 because 2 state vectors are here. This is the my B matrix, input is given with 0 and 45. So, it is given here with initial condition is equal to 0. So, we need to determine the solution of x t. So, if you remember from the previous concept, so our solution of x t is given by summation of z I r plus z s r. So, z I r was previously we used to estimate our state transition matrix phi t, and this is 0 state response. It means this is a response in presence of input. Okay. So, here it would be given by phi t dot b dot u if we discuss in time domain. So, in this question this u t is basically the step input is given. Okay. It is specified in the numerical that this is a step input is given and then we need to calculate x of t. So, it is given that initial condition is equal to 0, it means my z I r response would be 0. It means my solution x t can be determined by only z s r, that is phi of t dot b dot u of t. So, again I need to take the help of Laplace transform to obtain the solution. So, in Laplace domain this x of s would be given as phi of s basically and b dot u of s. Okay. And this u of s, because it is a unit step function, is given by 1 over s. B matrix is given to me, I need to calculate phi of s. It is Laplace inverse of s I minus a dot b dot u of s. Okay. So, I need to calculate first Laplace inverse of s I minus a. Okay, space is not there. So, we can do the calculation of s I minus a. So, A matrix is given to us. So, s I minus a, s I would be given by this expression. A matrix is given by this expression 0, 0, 0, minus 9. If I solve it, this will become s 0, 0 and this will become s plus 9. So, this is s I minus a, we need to calculate it inverse. So, for inverse I need to multiply with the mod of this matrix. So, this is the mod of matrix 1 plus s multiplied by s plus 9. Okay. So, this would be the mod of this matrix 1 over this multiplied with this matrix. This is the inverse, s plus 9 will come 0, 0, s plus 9 after adjoint operation, this will remain only s. Okay. So, this is the s I minus a inverse, right. So, now we need to solve it, multiply this, we will get 1 over s 0, 0, 1 over s plus 9. So, my s I minus a inverse is available to me, I have to multiply with b and u of s. So, here this expression would be written as 1 over s 0, 0, 1 over s plus 9. My B matrix is given, it is 0 and 45, 0 45 multiplied by 1 over s. So, I can directly multiply here, this will become 0 45 by s. Okay. And if I further multiply this matrix, this will gives me 0 over 45 over s multiplied by s plus 9. Okay. If you solve it, you will get like this. Okay. So, here this will gives me x of s. So, you can take the Laplace inverse of it. So, for partial fraction you can separate s and s plus 9 parameter. So, it will gives you two element. After calculating Laplace inverse of this, it will gives you x of t. The first element would be x 1 0, it is x 1 is equal to 0, second element x 2 equal to Laplace inverse of 45 s over s plus 9. So, you can calculate from yourself, it is very easy. So, in this way we can calculate the x t in terms of this ZSR, right. So, this is the numerical that can ask over this topic. So, now we will see the method to obtain the state transition matrix. We had discussed already the Laplace method. Now, we will come to the power series method. So, in the power series method, we have to use this expression x dot t equal to a x of t. So, here I am assuming that my current input is 0, because for state transition matrix we are knowing that our input is only initial condition. We are assuming that my external input is 0 here. Okay. So, that is why we assume that this is my state equation. Further, if I simplify it, x t equal to exponential of e of a t x 0, where e of a t given by this expansion we had discussed in the previous lecture. So, I am assuming that this x t is equal to this expression, okay, c 0 plus c 1 t plus c 2 t square plus c n t raised to power k. So, x dot t is given by this c 1, or you can say this whole expression of x t can be written like this, a dot of this a dot x t, this is a dot x t, okay, and this one is x dot t. It means I need to differentiate this equation with respect to time. So, this c naught will be 0, c 1 t will become c 1, c 2 t square will become 2 c 2, and this series will go on. So, this is x dot t equal to, this is x dot t, it is equal to 8 times of x t. Okay. So, now we need to compare here the coefficient of t. So, we will get here for t naught, we can say because t coefficient is absent here. So, I am assuming the power of t is 0. So, c 1 equal to a c 0. For t, you can say for t value of 1, I am assuming that it is t 1. So, it is 2 c 2 compare with here c 1 a c 1, right. In the same way for this coefficient comparison. So, we will get here value of c 2, we need to put here, and then we need to evaluate for c 3, and in the same way we need to obtain c 1 c 2 c 3 in terms of c naught. So, c 2 value we obtain in terms of c naught, c 3 value we obtain in terms of c naught by simple mathematics, okay, and c 3 equal to c naught, and now we need to put down in the above equation. Okay. So, in this equation we need to replace, if we see the equation number 1, this I assume the equation number 1, okay, where x t equal to exponential of e of a t x 0. So, if I put here time t equal to 0, so I will get here x 0 equal to constant, that is c naught. So, from equation 1, this is the expression. So, I calculated earlier value of c 1, c 2, c 3 in terms of c naught. So, I have to use those value. If you see c 2 in terms of c naught, c 3 in terms of c naught, okay. So, all these value we had calculated, okay, and c 1 equal to a c naught we already calculated. So, here we need to replace c 1 in terms of c naught, c 2 in terms of c naught, and then we will obtain this expression, okay. And here if I take common c naught, so this A is matrix. So, instead of 1 I will get here the identity matrix, this is the expression. If I further solve it, so this will gives me back again e of a t x 0, it is equal to exponential of a t c 0. So, we have to use this value in this expression. So, we need to compare the equation number 3 and 4, Okay. So, this equation is coming from the previous case, that is x t equal to exponential of e of a t x 0, and this x 0 is related to the c naught. Okay. After comparison, we are getting this expression. Okay. Simple comparison method. So, in this way we are getting this exponential of e of a t. It means we obtained here state transition matrix, where x 0 is c or c naught, that you can say. So, this is the state transition matrix from power series method. So, whenever we need to obtain the STM, we need to expand the series, and then with the help of series evaluation we need to obtain the exponential of e of a t. Once exponential of e of a t value is determined, we can say our state transition matrix is determined. Okay. Now, we are going for next method, that is diagonalization method. Okay. So, this method will convert system in, you can say this method has to convert system of state x to the different state of matrix. So, in the diagonalization method, we will get the different eigenvalues in the diagonal element, and those eigenvalues if we plot on the S plane, if they are lying in the left half, we can say the system is stable, or state variable or state space model is stable. Okay. So, this thing can be obtained by this method. So, x dot t equal to a x t, we are assuming that initial value x 0 equal to x naught. This is my previous definition solution, x t equal to e of a t x 0. Whenever my external input is 0, I am assuming that this A matrix having different eigenvalues lambda 1, lambda 2, lambda 3, lambda 5 till n values. Okay. So, assume a new state k where x equal to m k, okay, where x is the, you can say, ordinal state matrix, k is new state vector, and m is here a basic or model matrix. So, here k can be written as m inverse of x, or k dot, if I differentiate the above equation, so k dot equal to m inverse x dot, or x dot can be written as a x. It means x dot t can be written as a of x t. So, this thing is written here, okay, from this expression, and this m inverse a of x can further be written as a times of x equal to m k. If you remember, we had written here. So, this replacement we have done doing instead of x, this will come further. If we solve it, we will get this expression. Okay. So, here m inverse a m, if you calculate, this would be a diagonal matrix where diagonal element would be the eigenvalues of the vector or state A matrix that we assume. We assumed here lambda 1, lambda 2, they are the eigenvalues of A matrix. This will be the element of m inverse A m matrix. We are assuming it as A cap k, where A cap k is a matrix which involves all the eigenvalues as a diagonal element. So, this is the A cap matrix. Okay. So, k dot A cap matrix can be written like this, can be written like this. Okay. So, if we want to calculate solution just like the state transition matrix, so this will gives you k of t equal to exponential of A cap t k 0, same as we had seen for STM previously. If this is my state equation, this is the solution. In the same way, this is the state equation and this is the solution. What the difference, where my A matrix is a diagonal matrix which consists of all the eigenvalues. So, this is the expansion of series exponential of e of a t. This is my anti matrix, this is the A cap t, lambda 1, lambda 2 diagonal element, this is A square, A cap square is here, lambda 1 square, lambda 2 square, lambda n square, this is the cube matrix. Okay. This series will go on. If I sum this element 1 plus lambda 1 plus 1 by factorial 2 lambda 1 square plus 1 by factorial 3 lambda 1 cube, this will make a series here. It means we will obtain a series in the diagonal element if we sum it. Okay. And then we will obtain this expression, exponential of e of A cap t can be written as exponential of lambda 1 t, exponential lambda 2 t, exponential lambda n t. If we solve or if we compress all this diagonal element. Okay. So, in this way we can obtain this E A cap t. Okay. So, here this x t equal to m k t we had seen. Now, this k t can be written as this expression we had seen, right, and x equal to m k, how we are obtaining it. So, x 0 is given as m k 0, where k 0 can be written as m inverse of x 0. Okay. So, this is the case. So, here this k 0 we use, it can be represented by m inverse of x 0. You can directly take it from here, right. If we solve it, we will get this expression exponential of, you can say, because we know that x t equal to exponential of e of a t x 0. So, e of a t can be written as m times of exponential of e a cap t m inverse. Okay. So, we need to compare with this. This is my standard equation x t equal to e of a t x 0. If I compare with it, so we will get e of a t is equal to this much. Okay. Suppose this is the equation A, this is equation B. Compare the coefficient x 0 will remain same. The remaining term m e a cap t m inverse will be basically the exponential of e of a t. So, in this way we can obtain the e of a t. It means this is the STM given by this matrix. So, this is the diagonal method to obtain the state transition matrix, right. So, Cayley-Hamilton theorem, just I am leaving this because already we had seen Laplace method, power series method, and this diagonal method. It will help you to obtain the state transition matrix. Now, we will come for the controllability. So, whenever we need to observe whether our control system is controllable or not, for that purpose we have to go for controllability, right. It means if I am providing any input, any control action to my system, whether it is completely following it or not, it can be explained by the property of controllability. Okay. So, that is why we need to determine how easily my system can be controllable on the basis of this property. So, here we are having the state system, or you can say state space variable, and it may have various state vector x 1 dot, x 2 dot, or x 3, x 4. So, these state vectors are controllable or not on, or if it means if I apply certain input, then this state vector affects or not, it will explain by the controllability. So, higher the value of controllability, more stable would be my system. If controllability value would be less, then more instability will come in the system. Okay. So, here we need to do what? To check it, we need to apply a controlled input to my state space model, and then I need to see whether I am getting my final state that I desired. It means I am getting my desired state or not on the application of my input, right. So, this explains the controllability. Okay. The system is said to be completely controllable if every state variable of the process can be controlled to reach a certain objective in a finite time by some unconstrained control u t. Okay. So, here SFG is given. So, you can say here this is my x 2 dot, right, this is my input u. So, input u can reach to the x 1 state vector and can reach to the, you can say, derivative of x 1 dot and x 1 state vector, but it can't reach to x 2 and x 2 dot, right. There is no path. It means my input is not going to affect my state variable x 2 dot. So, we can say x 2 dot is not controllable. It means if I apply input, it will not change. Okay. So, we need to define a test which is a Kalman test, which will test whether my state space variable is controllable or not. So, in that case I need to define here a matrix, that is Q. It can be obtained by B, A B, then you can say it would be A square B, and it will, this power of A will go on. So, if I calculate this matrix and if it is not 0, if I calculate the mod of this matrix or rank of matrix, if it is not equal to, if you can say mod is not equal to 0, then my system is controllable. If mod of this matrix is equal to 0, it means system is not controllable. Okay. So, this thing is that we need to calculate determinant or mod of Q matrix, it should be non-zero. If it is 0, it means this system is not controllable. So, this example is here. Here I am assuming the state vector. I can take this is the A matrix, this is the B matrix. I need to calculate B dot B and AB matrix, okay, because it is going for 2. So, that is why we will not consider the third element. So, B and AB is our instruction, restriction. If we are going for third order matrix, if suppose A order is 3 cross 3, then we need to consider third element as A square B, that will make this Q matrix. So, here we are assuming order is 2 cross 2. So, we will take only 2 element, that is one is B, second is A B, we will not take here A square B. Okay. So, A B matrix given by this one. So, you can take this S, basically it is a Q depending on our observation. So, this Q matrix given by B A B, and here if I take its determinant, the value would be 0, it means the system is not controllable, right. This is the way to obtain the controllability of any system. Now, in the same way we will look for the observability. So, how my state vector changing the output, this term or this process will come under category of observation. Okay. So, the changes coming in the state variable is reflecting in the output state or not, it will be explained by the observability. Okay. So, here you can see again that my SFG is given here, you applied the input u, okay, and it is going to the x2 dot, it is going to x1 dot, it means my input is passing to the state variable x1 and x1 dot, x1 dot and x2 dot, it means both are controllable, but is it observable or not? You can see my output is here, the state x1 is directly going to the output, but my state x2 is not connected to the output. It means any change in x2 will change the value of x1, then it will reflect changes in the output. It means change in x2 is not directly available at the output. It means my x2 state vector is not observable. It means change in x2 is not reflecting at the output. So, this will explain here observability. Okay. It means change in state vector reflecting at the output or not, it will explain by the observability. Again, to determine the observability test, we need to calculate here output matrix C matrix. So, in the previous case of controllability, we were observing the B matrix, you can see we are dealing with B matrix input matrix. Okay. For observability, we have to look for the output matrix. So, here first row or first column would be my C matrix, transpose of C matrix, second would be A transpose C matrix, then third would be A transpose square C transpose matrix. Okay. So, this series will go on depending on order of my A matrix. If my A matrix of order of 2 cross 2, I will calculate only these 2 column. If my A matrix of order of 3 cross 3, I will calculate all the 3 column. Okay. So, in this way we can calculate observability of control system of any given system. Okay. Now, we will see the quadratic equation, how we can obtain this equation. Okay. So, quadratic equation basically plays a very important role in the definition of system. You can say in defining the or study the linear system. So, whenever we study in unit 4 about unit 3 or 4 about the root locus and other properties, we have to go for the quadratic equation. So, we will see how we can obtain quadratic equation from various method. One is we can obtain from differential equation. Suppose we are getting a differential equation like this. Okay. This is the function of y t, and on RHS we are getting function of input u t. Okay. So, I need to assume it as a homogeneous equation, it means my input is absent. So, I will make u t term equal to 0. So, I will get only this term if I am assuming it as a homogeneous equation. So, I am putting this u t term equal to 0, this will be my remaining expression, and this expression will gives me the quadratic equation. Okay. Now, quadratic equation can also obtain from transfer function. If transfer function is given to you in this method or in this manner, then you need to put the denominator polynomial equal to 0, then the expression obtained, that will be the quadratic equation. Okay. And the third method is here, you can obtain it from the state equation, you have to calculate C S I minus A inverse. Okay. So, if you solve it, you will get there the quadratic equation, right. If you get the S I minus A matrix, okay, if you take the mod of S I minus A matrix, this will gives you the quadratic equation, right. So, from this if you performing this step you will get S I minus A, in between you have to take the mod of S I minus A, this will gives you the quadratic equation. Okay. So, thank you for today. Remaining topic we will discuss in next lecture.